Good morning, Oregon. And those of you who are in the modeling business, if you see something that in any of these slides that looks familiar, like you might have seen it in another presentation, since I spliced together about material from 3 or 4 different past presentations, if you see something that looks familiar, that might be because you have seen it before. But unless you've seen everything I've ever presented at conferences and webinars and such, then hopefully there'll be at least something new here for everybody. And I am trying to see if I can get the, okay, did everyone see a change of screen just now?
Yes.
All righty, okay, yep. Yeah, what I'm going to do here, you probably saw it in the abstract in the agenda. I've broken this up into 2 parts because I'm putting travel time data really to 2 distinctly different uses for models. One of which is a straight base year validation, where I'm using average travel times by roadway segments. And then there is another part in the second half of the show here where I'll talk about how I've been making use of variability in travel times as part of estimating travel paths within modeling. And that came from a TRB paper that the model software developer and I presented at TRB 12 years ago. And probably noticed that, particularly with some of the slides I'll have later, that most of the work has been done with GPS probe data, which I think was what you all wanted to focus on. But since I've been working using travel time my entire career, including well before we had a massive deployment of this data, some of what I'm doing still goes back to floating car surveys, spot speeds, some of our permanent ATR stations that monitor speed, and that's all gone into the mix as well. And I still make some use of the floating cars, and I've got a slide about halfway down that will go into more detail on that. And then this, I guess, I'm sure a lot of you probably already know this part anyway, but the distinction is that with GPS data, that too has evolved over time. There you have a lot of, in terms of the sources of information, but in essence, it's from either vehicles or cell phones inside a vehicle that are spitting out waypoints that are both time and location stamps, sometimes at regular intervals, sometimes irregular intervals. And with the floating car, it was essentially the same idea. I mean, the user could specify, what location you wanted to write down, what time you had for at a location that was convenient for whatever your application was, which isn't always the case with GPS data, especially given depending on what kind of intervals your waypoints are coming out at. But the sheer amount of it's compensated for just by the sheer amount of data that we have available from GPS, and particularly with the connected car technology that's getting deployed out there, when you've got waypoints that are being emitted every 3 to 5 seconds. Some of our data vendors have also figured out that in addition to various other people that they're marketing this information to, they can go to the traffic engineers, the people who are looking at the performance of all the all the things that they're doing with traffic signal systems, and say, hey, we can give you all the metrics that you used to get from your before and after studies. So this field continues to evolve, but there's certainly more than enough for those of us in the planning and travel modeling industry to take advantage of it. And then there's always the question of why would those of us in this line of work be interested in looking at this data. And to me, I guess you can distill it down to two main things. The travel paths, there's been a lot of study over the years as to what things are more important than not. And I've always taken the position that the travel time is more important than other criteria, and I have a separate presentation that delves more into that I borrowed a one or two slides from here as well. And then particularly when it comes time to converse with our customers, the folks over in our TAC committees at the MPO or at the Public Works building, they talk in terms of the level of service metrics from the Highway Capacity Manual, and the metric that gets utilized for that is, more often than not, travel time and delay, including for urban streets. And those of us in the MPO world presumably are still interested in urban streets. And the other thing that I often throw in, particularly when there are modelers in the crowd that aren't necessarily familiar with the work I do, the work that I've done ever since I got started in this business has been considerably different than probably what most modelers in this country have been doing. And it just goes back to really the beginning of my career. I did not start my career in the kind of place, so a large organization, whether an MPO or a DOT, where you show up and you have a supervisor there who shows you the ropes and tells you this is how modeling is being done here, has been done for a long time, and what we expect of you. When I started off in the small MPO world, there was no one there to tell me what it is I was supposed to do. Just find a way to do it, figure it out for yourself, Sam. So it began there, but what I did have instead was, again, those customers over on the TAC committee and in the Public Works building who were not shy to telling me what it was that they took seriously or what it is they don't take seriously and why. So that was how I got started, and I've pretty much just kept going ever since then over the years. And and my interest in using travel time for validation as well as traffic counts starts really from that point of view. And I thought there'd be a couple of graphics here that would help illustrate the point a little bit, particularly if you're in the modeling world, if you're still relying on things like fixed roadway capacities and volume delay curves. Well, the graphic on the lower left there that I put together from all the information and all the travel time I've attached to our statewide model, all across the state of Ohio. Well, the difference between the red dots and the magenta dots that you see over there is telling you just how far away you are from being able to get the modeled travel time right, vis-a-vis what actually happens out there on the roadway. Now that data all comes from the PM peak hour, but there's also a temporal dimension to that problem as well, which I'm showing on the lower right there. The blue line going across the day you probably recognize as being essentially how much traffic volume there is out there at by time of day, and you can spot where the AM and PM peak periods are. The average travel speed by time of day that you can see at the top of the chart, well, that actually reaches its low point or point of the highest delay during the middle of the day rather than the PM peaks, or at least that's how it works out here in the slower growth Midwest. The big cities on the East Coast and the West Coast, that can vary, but this is the pattern in Ohio, and this including the counties that are part of the MPOs that I do work for. And why is that? Well, the people who are traveling in the middle of the day tend not to use the roadway system as efficiently as the people who are out there in the peak hours. Because if you're people who are going to and from work, they make the same trip every day. They take the same route every day, and they know what they're doing, know where they're going. A little bit more than the folks in the middle of the day are. Plus, there's more trucks in the middle of the day too, and so this is the sort of thing that I also make use of as part of dynamic traffic assignment. And let's see, next is, and this is just the reassurance that, well, does all of this work? Has all of this worked out for me over the years? And if it didn't, then I wouldn't have anything really to tell you. I think the modelers in the crowd here will recognize that the black line is something that came from a long ago Federal Highway report on maximum desired deviation between modeled volume and daily modeled volume and daily traffic count. And I never had much problem getting underneath that curve. Now, on the other hand, when you're talking with traffic engineers and people who conduct the traffic counts, well, as far as they're concerned, I need to be matching those numbers exactly, right? But the sampling error curve at least tells them what's realistic, and they start to understand that better in situations on projects where I've caught them trying to count the same location twice in the same year. And even with their seasonal factoring, there might still be 10 to 15% discrepancy in their count in the two counts in the same location in the same year. So then I can ask them, okay guys, which count was the real one? And then travel time error, I've divided this up into two parts, sort of the good old days, and then the next one will be the current days with GPS. Back when I relied on the floating car, how would I know when the travel time was good enough or not? And the 4 bars on the left are the MPO models that I developed, and I looked at the travel time. I decided, well, if I make use of the 95% confidence interval of the floating car surveys that I'm using, then if I manage to get the model error within the sampling error of the floating car studies, then I'll declare victory at that point. The 4 bars that you see on the right, those were the 4 times I was able to find a report done by another MPO agency out there that tried to do the same thing on their urban arterials at least, and I figure since they wrote a paper on it, they might be doing a little bit better than most agencies. But reading their papers, it looked to me like they were relying on those fixed capacities and volume delay functions that I mentioned earlier, which means you're kind of limited as to how well you can do. Or if you manage to get lucky in the base year, it may still have been more by accident than design. Okay, and here is an example of, this is the latest MPO model that I validated, and for travel times, I would aggregate up to roadway inventory or a vendor roadway segment, and I'll have a couple more slides on what those look like later. And again, here's the 85-15 standard. 85% of the time I'm within the model travel time is within 15% of the observed travel time. In this case, it's actually more than 95% of the time I've been able to make that standard. Now, combining data from the various travel time sources that are out there, again, still making use of floating cars, because unlike our GPS data, we conducted that in a way that we can separate out the intersection delay from mid-block travel speed. So it's still useful for the initial coding of travel speed on model networks. Then the GPS data sources provide route by route, segment by segment, the validation at specific locations. He, I think, is going to talk more about the MPM RDS data set, so I won't mention much here other than to say that, yeah, that's what we've been able to make use of, particularly for truck speed. So whenever we have truck penalties, or more specifically the on-the-clock portion of truck travel time penalty, I've been able to make use of the performance management data for that. And then the rest of it, particularly to get an extensive amount of roadway coverage statewide, we have a contract with a vendor. Actually, our Office of Traffic, ITS, has a contract that I've been riding along for free, I suppose, with the archive data, but they get real-time data for the network that you're seeing, particularly on the right. On the left, you can see that the TMC-based roadway coverage, if you're in a urban area over 500,000 people, you get pretty good coverage there. I work a lot with the smaller MPOs that tend not to get great coverage from that system, but the vendors network that they refer to as their XD network, you can see particularly on the graphic in the lower right, a lot more center line miles getting covered, and there are 3 metro areas you see there, one of which is over in the upper left, over 500,000 people. The other 2 are less than 500,000, and you can see in the graphic just how much of a difference that makes in roadway coverage. And now the next 2 slides I have here are really sort of a combination of what I've presented to our model user group here in Ohio, how I've been aggregating segments together, because from the XD roadway segments, sometimes the segments are a little bit too small than what we need for model networks, particularly and it can create problems with GIS conflation. Fairly large roadway segment in the model might conflate to a small XD segment, particularly if it's missing the critical intersection where most of the delay is. So I have several other slides I've reduced down to 1 to show how I've aggregated that, which I don't do for the freeways, because the TMC network coverage tends to get it to right where modelers want it to have, between all the way from one ramp to the next ramp. Now, the folks in ITS, when they want to know when stuff is happening out on the road, they would like to know where in a 3 or 4 mile segment of freeway between interchanges, something is happening, but those of us in the modeling world tend not to need that much granularity. And this is just a segment of roadway, a few segments of road in my neighborhood that shows how I'm making those aggregations of segments, which I'm also using on the validation in that graphic that I showed you a couple segments earlier. And that's the material I've put together on validation, overall validation using average travel time. As far as using the variability of travel time in addition to average travel time for estimating travel paths, this was done long enough ago so that we're still at the dawn of GPS data. So there are some floating car studies still around in the development of what I put together for some of my small MPO models. It was not, some of you might be familiar with the SHARP 2 effort to build up capability on travel time reliability, particularly within the modeling community. But the work that Alan and I described in that long ago TRB paper, that was not, even though it happened at the same time as SHARP 2, it does not come from SHARP 2. This was an independent effort, but there is one thing from one of the reports that I thought would be useful to show here, that when you're working with the variability in travel time as opposed to average time, the route choice has to be constructed a little bit differently, because instead you can't just add up, I guess to use the expression from the Statistics 102 class, the standard deviation of the sum is not the same thing as the sum of the standard deviations. So there's a different way that was certainly recommended here to how to put together a travel path and the statistics that allow them to be compared to other paths, which was called explicit route enumeration. We ended up creating a system within within this particular modeling software that allows for both additive and non-additive methods to be utilized, where one involves, you can simply add up link by link the standard deviations as well as the average times if you want, and use that as a basis to compare different travel paths. But the other one is simply trying to calculate a marginal increase in the overall standard deviation. Let's see, how am I doing for time here? Looks like I probably need to speed up a little bit here. Okay, so this, again, this is material that came from the TRB paper that I can certainly share with people who aren't familiar with it, but this is pretty much the higher order math that the model software developer put together that describes what I tried to describe earlier in English. But the middle bullet here about dealing with correlation of variability across links is a critical one for runtime, because if you tried to calculate how the travel time pattern on one link is connected or correlated with every other link in the network, then you have a model runtime that is just prohibitive. We're talking about days or weeks instead of the hours that I spend doing this. So Alan and I worked out a system where the correlations are only looked at, one, between adjacent links in the system, and two, only if it's if it's part of a through movement and not correlations on crossing streets at intersections. And this is just a little bit more elaboration on the how this gets done and the general equation that gets utilized, which came from some research that Alan found from a study in England. Again, we were pre-Sharp 2 on calculating this. So that was the general equation, and it varies by roadway classification because there are distinct differences between freeway and surface streets. Putting that together, and then this is just one of the menus as you step through setting up a travel model that lays all this out, including things like reliability ratio, which essentially says how important is variability in travel time to you, the motorist, compared to average travel time, which at least for my work, I decided to set as trial and error, depending on what the validation to traffic count seems to say it ought to be. And let's see, and so where's the data for this coming from? Again, we started with some work that was done in England, which involved an extensive amount of GPS data that already had been collected over there, both on motorways and what they call the A routes, which are like our arterials here. But one of the MPOs that I work with out here does pretty high sample floating car surveys, again, looking at the same points in time, same break points at signalized intersections, which found very, very useful to use to set up some of these relationships for urban arterials. And I even found that when I tried to just set up for myself a sample system, looking at the relationships between all these variables, the way they should be located, that ended up fitting the data that came out of their high sample travel time surveys very well, is what's shown in the highlight. And then here, what I did in the paper is just try to elaborate for a simple OD travel path between someone's home and where they work at the factory. There are, and let's say that there's 4 separate travel paths that you can take to get to the factory. The 3 different ways of estimating which path is the quote unquote shortest path can vary depending on whether you do this the traditional way in the chart below here. You just look at the average travel time, which incorporates the intersection delay depending on the type of control you have. This slide shows it the traditional way. Then this is the additive option under model travel paths based on reliability, where you're simply summing up the standard deviations by link. And you'll notice at the bottom, these numbers were considerably higher, but not only is the comparison, but a different travel path ends up being the shortest route. And then the last option here is if you do it in a non-additive way, where you just calculate the marginal added impedance at every link as road segment as you get to the destination. Again, you have a different estimation for every path of what the impedance is, and you have a different winner again in terms of what the travel path is. And if you've also, you may have noticed that it also means that the variability, the travel time early in the path, and means more in what path is chosen than what the travel times are later in the path. And while that was more statistical artifact than deliberate design on our part, I've always thought of it as something that made sense to weight the time and the delay early in the path as being more important than late in the path, because that's the point where you still have a lot more options available to you typically than by the time you get to late in the path and the choices are a lot much reduced. And this is the summary table for my first MPO model validation, where I tried to take, again, the reliability ratio, which method I'm using, and which data source really was used to develop the coefficient of variation equations, and just determine trial and error which one seems to match the traffic counts and the travel time data the best. And unfortunately, it's you can try to plot those out, it's not going to be the smoothest of surfaces here. You know, whichever, for each of those three variables, you know, the best option there seems to depend a lot on what the option was chosen for the other two variables. And these things don't always work out intuitively, but trial and error options are always there. And okay, I guess that was it. I guess I figured that was as much as I could squeeze into 30 minutes. And of course, there's plenty of other material I can provide people where all of that came from if you're more curious and want to look at more of it later on. But for now, if any of you have questions, I can take those now.
Hey, thanks, Sam. That's a information-packed presentation. So questions for Sam? So while
I don't know if there's a chat box. I haven't been able to notice it, but go ahead.
Right, I monitor that. There is no chat question at this point yet. So while everyone is thinking about their questions, I have one. So in your earlier slides, you're talking about the DTA, dynamic traffic assignment applications using validation. I think you in the slides you describe not application of DTA, not part of the basically four-step or ABM model. Can you elaborate a bit on that point?
Okay, let's see if I can make it all the way back to
right here.
That. Okay, so yes, I guess that's the third bullet here. Yes, this too is something that I probably didn't come at in the same way that other modelers across the country have done, because by the time my software vendor made this option available, I was already doing a lot of 1-hour static traffic assignments for impact studies for different kinds of land uses. Some of which don't reach their peak at the same time. I mean, studies for schools, you know, the peak hour there tends to be 3 in the afternoon. If there's a lot of restaurants on a particular roadway, the peak hour there might be, for volume, might be noontime. So it's not always right at 4:30 or 5 o'clock. So already doing a lot of that, and there's also a lot of situations where if you're looking at you know, sort of a moving wave, the top of the wave as you go from traffic that starts at the downtown offices before 5 o'clock, by the time it gets to the suburbs, it might be well past 5 o'clock. So how do you deal with issues like that? That was how I switched over to dynamic traffic assignment. And it's the The only thing I was doing differently from static assignment at that point is just running the assignments in sequence, hourly, 1 hour sequencing for the most part, where the travel paths, if they don't get finished by the end of the hour, then there's always the option that they might reroute depending on what the traffic congestion patterns are looking like by then. So, and I'm sure there's other things I could mention there, but that helps with the summary reporting of which locations are having experiencing their worst level of service when it's not happening at the same time of day. I also have one metro area where I do seasonal modeling, because their economy tends to be based on summer day trip tourism. If you know anything about Ohio, there's a relatively small urban area on Lake Erie that has one of the oldest large theme park, recreation parks. It's kind of like Six Flags, if you're familiar with that, except it's not a Six Flags operation. That's just, I'm using that term more generically. The name of the place is Cedar Point, but a lot of roller coasters, a lot of summer recreation, a lot of day trips. So it's not seasonal like Las Vegas or anything like that. Not that kind of recreation driven. So that's a place where, depending on where you are in town and how close you are to Lake Erie or to some of the tourist-oriented land uses, the worst level of service, the highest volume, might be summertime at 12 noon on a Saturday, or 1 o'clock in the afternoon on a weekday, rather than, instead of like it is if you're doing an impact study at a K through 12 school or a high school, where that will occur during springtime and probably 3 o'clock, or any place else that's well away from the tourist locations that might peak at 5 o'clock on a weekday in the springtime. So that's the dynamic traffic assignment. Conceptually is not much different than what I did for static, but it covers all the bases more.
Great, thanks. That makes a lot of sense. Questions from the audience? Feel free to mute yourself.
I have a quick question for Sam. Sam, in your earlier slides, you mentioned floating car method data collection. I assume you guys no longer do that, or do you still do that to supplement where you don't have probe data?
Most of the floating car data that we're still working with is circa 2000 in terms of when it was collected. And again, we're mostly using it for being able to code initial or free flow travel speeds on model networks before everything that is attributable to traffic control, curve and grade, railroad crossings, you name it. I didn't even explain a couple of slides that I had in there related to railroad crossings, which is a separate thing I'll do for TRB. But yeah, that's about the floating car. Is because we're using it for coding of networks. It serves a somewhat different function for us than the GPS data, which is mostly going for the validation side, roadway segment by roadway segment for travel time. We still occasionally will go out and do more floating car if somebody wants an answer fast enough. Say, what if we raise the speed limit on freeways throughout the state for either cars or trucks, which has been happening on occasion because of some of the issues we're dealing with statewide and with our toll road that goes all the way across the northern part of the state. So we haven't stopped doing them completely, but yes, in terms of it being a current data source for travel time, we don't use it very much anymore.
Thank you.